Okay, 1-4, continuity and one-sided limits. Continuity is what it sounds like, but there's some general rules on continuity. And then one-sided limits, I've kind of mentioned it a few times, but we will talk from the left and from the right. We won't always be both. Okay, so up at the top, this is the first example is called a removable discontinuity. And the reason why it's removable is because could I stick my finger right there on that hole and plug it up?
I guess.
Yeah? Okay. So anything that I can fix easy like that is called a removable. The next one is called a non-removable. Are they connected in any way? No. There's a big, huge gap, isn't there? That is clearly discontinuous. Yes? Yeah. Now, the third is called a removable discontinuity. Again, could I stick my finger right there and plug it up? It is, though, when the value of C is actually just different than, it's just off the graph. But it's still considered a discontinuity. So anything I can reduce out is a discontinuity. So if I'm factoring a rational expression and I can reduce out like x minus 4, where 4 would not be included in the domain. So 4 would be considered a removable discontinuity because I could get rid of it. So continuity at a point, if function f is continuous at C, if the following three conditions are met. F of C is defined. The limit as x approaches f of x exists. And the limit as x approaches C of f of x equals f of C. So direct substitution has to work. That's the third one. It's basically what that says.
How do we know if it doesn't work?
How do you know it doesn't work? Like
when no. Like when it's just like equal to 0 or it doesn't have an answer. You said when it works, but like.
Oh, no, that's not what I meant. And I was trying to figure out how to answer that question. Okay, the limit of f of x at C as it approaches C is the value at C. So it's the same. So the limit here, this limit at C would be, let's say, 7. But the value of f of C is 5. So that's discontinuous.
Okay.
That's what I was trying to say and didn't say it very well. Thank you for asking the question because that needed some clarity. Continuity is on an interval. So we talk about, if you look at the pictures before, it's on an open interval. These are not brackets. It's not a closed interval. It's an open interval, meaning they're not included. We talk about it on intervals. If it is continuous at each point of the interval, the function is continuous on the entire number line, where you have functions that are continuous on an open interval, and then you have functions that are continuous everywhere. And it just depends what happens everywhere on a function. Am I good?
Yeah.
Okay, so discuss the continuity of these. Well, on the first one, we have f of x equals 1 over x. What do you know about that?
I know that x cannot equal.
Okay, so we know that x cannot equal 0. Yes? So that is a vertical asymptote.
Yeah.
Okay, so we know that at 0 it looks like this, yes? So this graph actually looks like this and like this. But is an asymptote a removable discontinuity or a non-removable? It's non. I can't fix it, right? So it's a non-removable. Okay, it's a non-removable discontinuity because I couldn't reduce it out. It's an asymptote. It is there. It is the wall. Okay, so let's look at B. I would hope you would immediately factor, yes? So I know that x can't equal 1, don't I? But what happens to that x minus 1 and that x minus 1? Do I remove them from the situation?
Yeah.
Yes. So if I were to graph this, it would be something like this. Correct? So this is a removable discontinuity. It's kind of making sense. Okay, so this we have a I can't even speak. Piecewise function, yes? And the point at where they join is 0. So when it's less than 0, it's a line that has 1 as its x-intercept and a positive slope, positive 1 slope, yes? So it looks like this. And it could imaginarily go off to the right, but it doesn't work there, does it?
Yeah.
Now the next one, I have a parabola that the vertex moves up 1. So it's still going to hit here and come up like this. Now, for the first equation, I had a closed point. Oh my gosh. A closed point at 1, didn't I?
Yeah.
But the second one is open, so it's not in both functions at one time. But is this discontinuous anywhere? Are there any gaps, holes, sharp turns? No. So it's continuous. And then they say on entire real number line, I say continuous over all real numbers. What's sine look like? Is there any asymptotes? Goes like this, yes? So how would you describe its continuity?
Yes.
Would it be the same as here?
It's overall real numbers.
Okay. Okay, so one-sided limits are exactly what they say. They are one-sided limits. I look at things from the left and I look things from the right. So when I have down here in the blue box, I have the limit as x approaches c from the right of f of x is some limit L. When that positive or negative is off to the right-hand side of the number, that means from the right or from the left. And if it's a negative over there, it means from the what? Left. Then we also have the limit as x approaches c of f of x. So the first one we are looking from the right. The second we're looking from the left. And on this one we're looking from what? Both directions. So in order for the limit to exist at C, the right and the left have to be equal. And we've already been doing left and right hand limits, haven't we? But I haven't specifically just asked for one of them. Am I good? Okay, find the limit of f of x as it approaches -2 from the right. So we would write that as the limit as x approaches -2 from the right of the square root of 4 minus x squared. Well, -2 from the right means you follow the graph from the right, and what is your y approaching?
Our y.
Mm-hmm.
2.
Mm-mm. The y's are what you
0.
see. The y's are 0. So the answer is 0. There's not much explanation that I could give for this. Go from the right or go from the left? Good?
Yeah.
Okay, this function is called the greatest integer function. And kind of looks like an absolute value, but it's double-sided, like the double-backed R. Also known as a step function. Okay, so I have 0 houses until I have 1 house. And I have 1 house until I have 2. I have 1 car until I have 2 cars. Things like that. Usually things. Does that make sense? Okay, is this continuous? No. This is a discontinuous function. It skips around. So if I want the greatest integer of 2.5, the answer is 2. Because I have 2 until I have 3. So the greatest integer of negative 1.999.
-1.
I have negative 1. No, negative 2. Brain has to go backwards. Because negative 1.9 is actually over here. Actually, like clear over here. See that?
All right.
I threw in the negative just to screw up our brains, and then I screwed up mine too. So that's what it is. It can move h and k just like any other function we have. We tend not to do a whole lot with it, but there's like 1 or 2 problems today. So twist your brain a little bit. Okay, this is if a limit exists. There's a lot of words here. It basically says a limit exists at some letter C. So the limit of x approaches C of f of x only exists if from the left and from the right you have the same value. Okay, did we not go over from the left and right has to be the same? If it approaches 2 different values, the limit does not exist. Correct? So they basically just said, don't forget this. Let's confuse you some more.
Yeah.
Okay, definition of continuity on a closed interval. A function is continuous on a closed interval Now remember I said parentheses was an open interval. They don't include the endpoints. Closed interval includes the endpoints. Okay? So this includes A and B. So I have A and B. There's my graph. If it is continuous on the open interval. So basically it's only continuous if you close it, if it's continuous if you open it and put open circles. That's it. The function f is continuous from the right at A and is continuous from the left at B. That's it. That's all it's saying. Okay, discuss the continuity.
Well, it's continuous from the right at 1.
Okay, so when I go -1 towards -1, I get 0, yes. And f of -1 is 0 also. And when I go to 1, I get what? 0. And f of 1 is 0. And so is it continuous?
Yeah.
Okay, if it isn't one of you shaking the whole room, it's the other. I'm just trying to write. Okay, what else do we got? Okay. This is so... Sometimes I'm just like, why do we have to put this? These are in there. They are boxes. I want to talk about them with you. I don't know how much you really want to say. It looks like it's cut off. Okay, Theorem 111. It's properties of continuity. If B is a real number and f and g are continuous at x equals c, the following functions are also continuous at c. So if f and g are, but it's continuous, so the scalar multiplication, if I multiply f by any scalar, it's not going to change its continuity. If I add the two, if I take two things that are continuous and add them, isn't their sum or difference going to be continuous? Makes sense, right? If I take two things that are continuous and I multiply them, is it going to be continuous? Yes. Now, quotient. The answer is yes, except where? Where g, or where the denominator is equal to 0. The following types of equations are continuous over their domain. Okay? So if it's in their domain, they are continuous. If it's out of their domain, they're obviously not continuous there. So any polynomial is continuous. My domain is all real numbers, correct? So as long as it doesn't have a denominator in it, we're all good. Or a fractional exponent. Okay, any rational number is continuous over its domain. So that excludes anything that we take out of its domain. Doesn't it? Any radical is continuous over its domain. So any even radical, its domain does not include any negative numbers, but it's still continuous over its natural domain. Any trig functions, again, over their domains. Sine, cosine are all real numbers. Their domains are all real numbers, yes? But tangent is x cannot be equal to pi over 2, right? So pi over 2n. So pi over 2, 3 pi over 2, and anything. So when it has an asymptote or a restriction on its domain, it's not continuous there. And that should just really kind of make sense. It should be intuitive with that. Did I jump twice? No. Okay, the intermittent value theorem sounds like it's a lot. It is not a lot. It says if f is continuous on a closed interval and f of a does not include or equal f of b, k is the number between f of a and f of b, then there is at least one c in AB such that f of c equals k. Okay, the pictures make so much more sense. So I'm telling you that over the closed interval a to b, So A to B. This function is continuous. F of A does not equal F of B because F of A is clear up here and F of B is clear down here. So they don't equal. K is some random number here. And we actually have 3 values where the function 3 times where it's the same. Do you see that?
Yeah.
Okay. So now we're not continuous over AB, are we? We are not. And here's K. Is there any value where F of C equals K? No.
No.
So if it's continuous, there's going to be at least how many?
3.
Nope. 1. There's going to be at least one number. Can it be 1,000? Yes. But there's going to be at least one time where it equals K. If it's not continuous, it's not. That's basically it. Sometimes I think they give you words that just go, what? Okay. Use the intermittent value theorem to show that the polynomial function is weirdly placed in the middle of the screen. F of x equals x cubed plus 2x minus 1 has a 0 on the interval from 0 to 1. So how we're going to do that is we are going to tell me f of 0 is what?
1.
1? Okay. Because we're looking at the interval of 0 to 1. And I don't know why I wrote it clear down there. That's weird. Okay, f of 1 is what?
F of 1.
1 plus 1 minus 1 is,
Plus 2 minus 1.
oh, how about 2?
2.
It's 2? Okay, so the intermittent value theorem said if it's continuous, so is x cubed plus 2x minus 1 continuous?
Yeah.
Yes, because what kind of a function is it?
A cubic function.
Well, yes, but it's a polynomial function, yes? And a polynomial function, its domain is all real numbers. So it is continuous. So continuous, check. Yes. And then f of 0 is not equal to f of 1. So that's a check, right? So, did it not say, let me read it to you again, if f is continuous on a closed interval a to b, and f of a is not equal to f of b, and k is a number between f of a and f of b, so is k has a 0, right? So the value is going to be what? What's a 0? What's the k value? What's the y? Because k went this way, yes? So what is the y value right here? 0. So k equals 0. Is 0 greater than how did I say that? I wanted to say it. Because I'm going to say 0 between 0 and 1. And the answer to that is no. So, can you guys see when I pop up the eraser? Does it show on your screen? Probably not. So, I want to know if this function goes in between here. Does it?
Yeah.
So, f of 0 is 1. actually, f of 0 is not 1, because the answer is no compared to this stuff. Because the answer, I have 1 and I have 2. So if f of 0 is 1 and f of 2, I'm going to put this here, is f of 0 is 1. Actually, let's put it where it goes. If f of 0 is 1 and f of 1 is 2, is there a 0 in between those two things? No. What's wrong with f of 0, guys? I went with it. It should be -1, shouldn't it? So now let's look at that again, because this is not here, is it? It is down here. So if f of 0 is -1, is 0 between -1 and 2? Is that statement true?
Yeah.
Yeah. So there's at least 1 point that this happens at. Now, we know that this equation only crosses the x-axis one time, correct? Because it's a function. But what if we didn't know that? Could it have gone like this? Could have had a bunch? It could have, right? It doesn't, but it could have. So is there a point? Yes. And we could find that point too. Well, do we need to find the point? Nope. It doesn't tell me to find a point, does it? We just proved that there was.
Are there any questions on the homework that has us find the point?
I don't think it does. I just think it has, like, what do we got? 83, 105. No, it says verify that the intermittent value theorem applies to the indicated interval and find the value of C generated by the theorem. But it says f of C equals 1 or 6. Oh, I didn't have the directions on there for us. Okay, so it'd be something like this. Okay. So it says verify the intermittent value theorem applies to indicated interval to the end of indicated interval and find the value of C guaranteed by the theorem. So again, is it continuous? Yes?
Yes.
So it's continuous. Check. F of A, and A is 0, is 8. F of 3 is 9 minus 18 plus 8,
Yeah.
-1.
-1.
Okay, so F of 0 does not equal F of 3. So, and you have to prove these things. So that's a check, right? So there is at least 1 point, is there? Isn't there? So now we have to figure out the x where y is 0. So 0 equals x squared minus 6x plus 8. So factors of 8 that add to 6.
1, 2.
So -4 and 2. So x equals 2 and 4. And is one of them between 0 and 0 and 3 in my interval? Is that what you meant? Is that what you meant? Yeah. Without that extra, like, what is the value? You can't find it. That's all you do on those.
Okay.
Questions? I know it seems tedious to say continuous and to show that it isn't, but if these conditions are not met, you can't use it. I think that's it. That is it. And actually, you have the notes